dude?
Kirchhoff.
Mr. Epic Beard. Oh yes, Epic Beard. And we went over this before the lab, but we're gonna just sort of go through it a little more slowly because it's important. Things that will be on the test, right? Adding up capacitors. Yeah. Kirchhoff's law problem, much like the one we did in the lab. So that's the first two things that'll be on the test. Third one will just, who knows, it'll be a wild card, okay? But you will need to add capacitors. Actually, it'll probably be on RC circuits, which we'll get to at the end of this chapter. Okay. Kirchhoff's laws. So, anybody remember anything about what this guy did?
He's German.
He's German.
With an awesome beard.
Not really much of an accomplishment.
That's not what the Germans said. They started a war over it.
Yeah.
He has laws.
He had some laws.
Yes.
The two important ones. He was a pioneer of electrical circuits and spectroscopy. And anybody know what black body radiation is? You will eventually. Okay. Let's talk about the first one. That's Kirchhoff's junction law. What's Kirchhoff's junction law?
Current in.
Current in equals current out. There we go. Okay. Junction law comes from conservation of charge. Conservation of energy gives us the loop law. So this is, and I know that we're kind of going through that a little bit fast, but it's not very exciting. It just has a lot of words. Okay. Kirchhoff's loop law says what?
Sum of the voltage or potential voltage equals 0.
Yeah, the sum of voltage differences across elements, if you go all the way around a loop and end up back where you started, gives you 0, okay? And we did a whole lab on that, and you guys did pretty good on it, actually. So, that's the idea. If you want to graph this, you can go through this loop, starting with this wire below the battery. Battery picks potential up, okay? Wires don't change potential as long as they're ideal. And capacitors bring potential back down, and so on and so forth, okay? So this would be delta V for battery 1, for resistor 1, delta V for resistor 2, delta V for the battery. You add these things all up, and you get 0, okay? So remember, the directional stuff, how you get the signs, is for a battery, when do you have a positive change in voltage? Which way do you?
It goes opposite. Yeah, when it goes positive to negative.
Negative to positive. When you travel, remember you have the current and the direction of travel. Okay, current, direction of travel. Battery doesn't care about current, okay, just direction of travel. So if the direction of travel is from the negative terminal of the battery through the battery to the positive terminal of the battery, that is considered a potential increase or a delta V positive. And batteries are easy because, one, you don't have to keep track of current, and two, when you look for the change in V, it's just a number for the most part, okay? And if you go the other way, it's negative. All right? Resistors are a little bit trickier. That depends on the relative directions of the current and direction of travel, okay? So when you're traveling with the current, is that going to be positive or negative? Negative, okay? So delta V is negative, and because of Ohm's law, delta V is equal to IR, okay? If you're traveling the other way, delta V is plus IR, okay? So that's the general rules for loop law with resistors, all right? Now remember, loop law also works with other circuit elements, any circuit elements. So loop law works with capacitors. We haven't talked about inductors yet, but loop law works with inductors. So we can go through the sign convention and stuff of those things. Later we'll use them to derive different things we use for circuits, like the charging and discharging patterns of RC circuits, right? So when you charge and discharge a capacitor, you can start with loop law, and it gives you a differential equation that you can solve to get the answers to that, okay? So, how do we use it? Let's start with the very most simple case of the circuit, okay? here's your battery, here's your resistor. If you want to calculate currents, you can just use V equals IR in this case. But if you want to look at it from a loop law perspective, you know current's going this way. All right? And do you have to know which way the current's going to use this? No. Right? You just have to guess which way the current's going to use this and then be consistent with your sign conventions. All right? So, you go around. The delta V here is just the potential of the battery. The delta V here is going to be minus IR, okay, which means E minus IR is 0, and you end up with basically Ohm's law.
Is it as E?
Yeah, it's squiggly E. It's not epsilon, it's kind of epsilon.
So that's not a constant?
There's 2 epsilons.
Wasn't one with a K?
No, it's not.
Or whatever.
Okay, so just bear with me.
Am I tripping?
Squiggly epsilon is EMF. Okay? Not squiggly epsilon, which in LaTeX, probably not. It's called var epsilon, which means a variation on how you write epsilon. Okay? This is permittivity. Okay? They are not the same because we are all out of letters. Okay? Also, EMF stands for electromotive force. Is it a force? No. What is it? Yes, confusing. It's an electric potential in volts.
I didn't write all that.
So this is the same as a delta V. Whatever. Okay? It's kind of an old notation, but it won't die. So here we are. Okay? As you've noticed in physics, we like to do things based on historical reasons, which no longer make sense half the time. And if you taught physics in a Western country, it's very biased towards European people. There's a lot of math and physics that was done in Asia and the Middle East, which we ignore because we're assholes. Okay. But actually, one of my projects over the summer is to go and find other people who did this same work in other places and incorporate it into the slides. The first thing I did was I made all the old white guys look younger, because that's when they actually did the work, right? Just so you know. But yeah, there's a lot of what history is told by the victors, right? So anyway, loop and junction law. Yeah, just when you thought like science and math was safe from the humanities and social stuff, it's not. Nothing is safe. All right. So Kirchhoff's laws, we have 2: loop, junction. Okay, current and voltage, and you need both of them to solve a lot of problems. All right, but they're pretty straightforward. This is like the least horrible thing in this class. So anyway, here's a quicker question. And you'll notice something nice happened here. Do you have to do IR for these? No, it did it for you, so don't be confused about that. Or D. Please discuss. We'll vote again. Much better. Okay. So yeah, it's going to be a 2-volt increase. If you want to look at this, this is going to be, the current's going this way. Is this positive or negative 8?
Negative.
Negative 8. Well, assuming we're traveling this way.
Yeah.
Okay. So negative 8 minus 6. What's that? Negative 14. That's plus 12. So that means we're at negative 2. That means that has to be positive 2. And it works both ways because you go the other way. This is plus 6, right? Plus 8, that's 14. Then you don't know what this is, and then you have minus 12, and to get 0, this would still have to be minus 2. But this would have to be 2 volts. Well, this is a very well-worded question, but you guys seem to figure it out. All right. So, we already did this.
Okay, let's try Kirchhoff's law out on a fairly straightforward problem. This is only one loop, so we're going to use the loop law. We don't have any junctions that do anything interesting, and so we know because everything in this circuit is in series that the current has to be the same everywhere. So we'll start with our protocol. Step 0, don't panic. Step 1, draw a picture. And you can see from looking at this that the picture is pretty well drawn for you. But there's a couple things we need to remember when we're doing Kirchhoff's law, and that is that first off, we have to pick the current. So we're going to pick the current to go this way. And that pretty much means that the current's going this way here, this way here, this way here, and this way here. And I'm going to tell you something that's going to sound a little bit strange, but it turns out even if this is not the direction the current's going, it doesn't matter, and I'll show you why when we get to the end of this problem. The other thing we need in order to determine all our signs is the direction of travel. So we're going to make the direction of travel this way. Okay? So both current and travel are going to be counterclockwise. And we'll see how this affects our signs as we go through the problem. So we're going to start with our battery over here. So this is 6 volts, and we know that this direction of current and the direction of travel point the same way, but for this particular thing that doesn't matter. So all that matters is the direction of travel points upward through the battery. And because it points upward through the battery, that gives us positive 6 volts. Okay? Then we get to our next thing, which is the resistor. The resistor, we care about both the current and the direction of travel. When these things are going the same way, we get a minus voltage. When they're going different ways, we get a plus voltage. So because in this case, this direction and this direction are both going the same way, we're going to get a negative. And voltage we get from Ohm's law, so we know the voltage for this 4 ohm resistor is going to be I times R, which is 4 ohms. Okay. We also know if we go through this battery, we're going to go through it backwards. So from plus to minus instead of minus to plus, that's going to give us a negative 9 volts. And the only thing that matters with batteries, remember, is the direction of travel, not the current. So we don't actually have to worry about the current through the battery, even though we know it's going down. And then when we get over to this lovely 2 ohm resistor, we see once again that the current and the direction of travel are the same way. So this means we're going to get a negative current times 2 ohms. That is our V, delta V, is equal to IR. Ohm's law. So when we add up all of these voltages, we sum up all of these voltages, we should get 0. And that's our statement of Kirchhoff's law. So that's when we write our equations. We know that the sum of all the delta V's should be equal to 0. Well, here's our sum of all our delta V's, and it's equal to 0. Our unknowns, that's pretty much just the current, and you can see we can change this so it's easy to see which things have this variable. Oops. Okay, so now we're going to rearrange this stuff. And we're going to solve for current. So we would solve this symbolically, but it's not really that much stuff. So it's easier to write things in this case. We want to guess, though, before we solve this, about what we expect to happen. So before we even go through the math on this, let's think about this. Which way do you think the current should actually go? We know this battery is actually bigger than this battery. So if you were going to bet on one of the batteries to win and push the current out of its positive side towards its negative side, a good bet would actually be that the 9-volt battery is going to win. The other thing, since this is one loop, even though these resistors and batteries aren't directly in series, it'd be a good guess to think that this is like a 3-volt battery with a 6 ohm resistor. So if we just do our V equals IR, and we solve for I, that means we're going to get about 3 volts divided by 6 ohms, and you can guess that that's going to be a current traveling counterclockwise. So about 1/2 amp, and that's going to be counterclockwise. So this is just our guess. Now when we solve over here, hopefully we're going to get the same thing. So we'll start and say, get 6 minus 9, and that's volts, is going to be equal to 2 plus 4 ohms times I. Well, this is going to give us negative 3 volts is equal to 6 ohms I. So I is going to be equal to negative 3 volts over 6 ohms, also known as negative 1/2 amp. So you see, since we picked our current going in the wrong direction, we get this negative sign over here. And so, like I said, it doesn't actually matter which way we pick our current because we're always going to get the correct answer. So we plugged in the numbers after we solved symbolically-ish. And this answer makes sense with our guess, okay? Because we picked clockwise, and this negative tells us that our current goes the other way.
When analyzing a circuit, first you want to make sure the drawing of the circuit makes sense to you. Okay, if it doesn't, redraw it so it looks better, it's easier to understand. Because circuit diagrams, there's lots of ways to draw them which are technically correct, but the whole purpose of circuit diagrams is to make it easy to understand what's going on. So if you have a circuit diagram that's not easy for you to understand, redraw it so that it's easy for you to understand. Okay? Then you want to guess the direction of the current flowing through each wire, and you want to indicate that on your drawing. And I cannot impress this upon you enough because I will not mark you off if you don't do this on a test. But if I don't know what you're doing on the test, I cannot give you partial credit. So it's very important to draw these arrows. That way, if you screw up the signs, I know if it's a math mistake or if you don't know what you're doing. Okay, because remember, math mistakes, you don't lose that many points. If you don't know what you're doing, you lose a lot of points. And if I can't tell that it's just like, oh, you just dropped a sign, okay, then you lose a lot of points. If you just screw up like one sign, but you drew everything correctly, you only lose half to 1 point, okay? So just keep that in mind. Travel around the loop in the direction of your choice. Now remember, any loop you could pick clockwise or counterclockwise, it does not matter. It also doesn't matter whether you guess the current right or wrong, because if you guess wrong, what happens? You just get a negative sign at the end, okay? So as long as you pick the currents and you stick with them till the end, you'll get the right answer, okay? So you have to guess the currents, you have to pick a direction for your loop, because remember, you have to pick a direction for current and for travel, okay? The main rules you have to follow is current has to behave like current, where it doesn't change until it hits a junction, all right? Then we want to label the delta V across each element, whether it's a battery or a resistor, making sure to include the correct sign convention from that chart on the previous page. Okay? And then we want to use any of these, basically loop and junction law, sometimes Ohm's law at the end, to solve for all your delta V's, meaning your potentials, and your currents for anything that you're looking for. Okay? So we're going to go through how to do this again. I know we already did this problem, but it's worth readdressing, and we'll go over in more detail how you put this in.
So now we're going to find the current through and the potential difference across each of the resistors in the circuit shown below. So how many resistors do we have? Well, we have R1, R2, and R3. So we have 3 resistors, and then we want to figure out how many currents we have. So we're going to go through our process for solving a problem. The first thing we want to do is draw a picture. Now here we once again have a pretty good picture, but we could probably make it better. So let's draw it just so it's a little bit cleaner. We have a resistor that's 4 ohms. We have a battery, make sure we keep the right direction, that's 12 volts. We have another resistor in the middle here. That's 2 ohms. And we have another battery facing the other direction. That's 15 volts. And then we have one more resistor. That's going to be another 4 ohms. So we'll call, let's label them with a little bit different color. Call this one R1, this one is R2, and this one is R3. All right? And we're going to just get rid of this thing so that we can have more space. What we want to do here is we want to check out what the different currents are for this circuit. So looking at what we know about currents, remember we have these 2 junctions. So here's a junction and here's a junction. And a junction is anywhere where these wires come together. So you can see at each junction you have about 3 wires coming together. So that means we have at least 3 currents. So let's label these currents. So this is going to be one branch of our circuit. This is going to be another branch of our circuit. And this is going to be the third branch of our circuit. So each of these colors has its own current. And so when we actually pick our currents and we label them, we're going to use these colors to keep track, okay? And you can label your currents IA, IB, IC, but what's really important is when you have more than one current, don't call them all I. Current goes this way. We'll call this one IC. And we'll get this current going to this other one. We'll say it's going down, we'll call this IB, and then we're going to have another current flowing this way, and we're going to assume this one goes this way just because of the way the battery is going, but remember it doesn't matter which direction we pick our current to go, and we'll call that one IA. So here's how we're going to set this up. We're going to do loop and junction law until we have all of our different currents set up. Okay, so we can start with the junction law. So the junction law comes from these little junctions. So we look at each junction and we look at all the currents going in and all the currents coming out, because remember, sum of current in has to equal sum of current out. All right, so using the junction law, we're going to look at the currents going in. Well, which currents are going in? Well, the current going in is going to be IA. And the currents going out, well, that's basically all the other currents. So currents going out, that's going to be IC and IB. So here's our junction law. Now you'll notice if we look at this other junction, we get pretty much the same thing. Currents going in are IC and IB, and then current going out is IA, but you can see this is the same equation as this, so we don't actually need to do it again. And this is a redundant equation. So you can get 2 junction equations from your 2 junctions, but they're not necessary. So we'll call our junction equation our first equation in our system. All right, so we've exhausted what we can do with the junction law, but now we want to use loop law. And loop law says when we sum up all the changes in voltage, we should get 0. Okay, so we have actually 3 different loops we can go through. So I'm going to look at these. So here's loop 1. Right? Here's loop 2. And then you can actually go all the way around the outside for loop 3. Now you'll notice when we add up loop 1 and loop 2, it's going to turn out that loop 3 will give us the same stuff as if you put loop 1 and loop 2 together. If you've taken linear algebra, this is called a linear combination. So just like with the junctions, where even though we had 2 junctions, it only gave us 1 equation, now we have 3 loops and it's only going to give us 2 equations. But look, we're looking for currents, and so since we don't know the currents, those are our unknowns, we have 3 unknowns, we're going to need 3 equations. So we only need 2 loop law equations in order to solve. So it turns out also you can make these go clockwise or counterclockwise. I've just chosen clockwise because it's simple, but you don't need to choose these loops to go clockwise. So I'm going to call this loop loop 2 and this loop loop 3. So if we look at loop 2, we're going to go around the loop. We'll start with the battery. So the battery, we're going through the battery from negative to positive. That gives us a plus 12 volts. Then we get to resistor 1. You're going with the current. So current's going up and we're traveling up because our loop is going clockwise. So that's going to be minus IAR1. Okay? And then we get to R2, and that's going to be also minus because we're going the same direction as current, minus IBR2, and all of this should add up to 0. So I'm just going to change these colors so they're easy to remember, and we can see a nice color. So this is IA. Remember IB we chose to be purple. And this is a good thing to do when you're learning these, just so you keep track of your different variables. Okay? Well, now we're going to do loop 3, and you can see for loop 3, let's start with the battery. That's usually a pretty good place to start. So we have 15 volts because we're going, once again, from negative over here to positive over here. So as we travel through from negative to positive, that gives us a positive voltage. We don't care which direction the current's going for batteries. Then we get to R3, and we're going the same direction as current. So that's minus IC R3. And then finally we get back to R2. But here you'll notice the current through R2 goes down while the direction of travel goes up. So in this case we end up with plus IB R2. And this, we have 3 equations and 3 unknowns. All right. So we're going to zoom out a little, and then we're going to deal with just these equations. So we're not going to do a ton of algebra. It's 3 equations and 3 unknowns, but we can solve this pretty nicely. So what we're going to do is we're going to use our understanding of matrices to make our lives a little bit easier. So we're going to rearrange all of these equations. So at this point, after doing Kirchhoff's laws, you've done most of the work, and the rest that we have left is just algebra and calculations. So we're going to do some algebra to get things into a nice matrix format. What we're going to do is try to line up all the currents, and let me show you what I mean. So we want to rewrite this equation as IA minus IB minus IC equals 0. Then we'll rewrite this equation as R1 IA plus R2 IB plus 0 equals 12 volts. And then finally, we'll write this equation as 0 plus, oops, in this case it'll be minus R2 IB plus R3 IC equals 15 volts. And all we've done is rearrange these equations, but I'll show you why. Here you'll see the ICs are all in one column, the IAs are all in another column, and the IBs are all in this column. And there's kind of this ghost IA next to the 0. and this sort of ghost IC next to this 0. So when you write this out in a matrix form, you can write it like this. So you'll just write the coefficients: 1, minus 1, minus 1, R1, R2, 0, 0, negative R2, R3. And you could see using matrix multiplication, this would be IA, IB, IC. It's going to be equal to 0, 12, 15. And you can see here we've just preserved this structure so that this matrix with the currents in it times our coefficients of resistors gives us our actual voltage. Now once you have it like this, you can rewrite this as an augmented matrix. And this, then we can plug in our numbers. So R1 is 4, R2 is 2, and R3 is 4. And what we're going to do here is put this into our calculator as this matrix. This is a 3 by 4, and we'll do reduced row echelon form on this 3 by 4 matrix. This thing is just for our reference, but when you actually write the matrix out in the calculator, you don't need to do that. Let's make this a little smaller so we have some space. Okay. So when you actually solve this and you get your reduced row echelon form, you'll end up with something like 1, 0, 0, 0, 1, 0, 0, 0, 1. That's your diagonalized matrix. And then your answers will end up over here. So that's going to be 3.19, negative 0.37, and 3.56. Now you'll notice this looks just like this. IA, IA, IC, IC, and this is going to be your IB. So IB, IC, and IA. Alright, and this is much easier than going through and doing all of this math by hand or trying to like do a bunch of terrible algebra. And you can always use a calculator on your test. Oh, there's going to be a negative here. Okay, so what does the negative tell us? The negative tells us that we have chosen the wrong direction for IB. IB is actually going up, but that's okay because we don't need to redo the problem. We know which way things are going. All right. The other thing it asked us to do was find the voltage. So now that we know that what the currents are, in order to get the voltage across your resistor 1, because remember this one goes with resistor 1, this one goes with resistor 2, this one goes with resistor 3, and we know delta V is equal to IR. So we're just multiplying this by 2 or 4. So R1 is a 4 ohm resistor, so 3 times 4. This is going to give us a delta V1 of 12.8 volts. This is going to give us a delta V2 of 0.75 volts. And this is going to give us a delta V3 for resistor 3 of 14.2 volts. So remember, R1 and R3 are both 4. and R2 is 2 ohms. So we have all of our currents and we have all of our voltages across our different circuit stuff. All right, so if you look back at this whole problem, you can see we use the junction laws, we used 2 of the 3 loop laws, 1 of the 2 junction laws, and we used it to find all of the different values we were asked for. So the last thing we need to figure out is, does this make any sense? So if you're looking at these different loops, the batteries really tell us which direction the currents go. So it's pretty obvious that we picked current A in the right direction because this 12-volt battery is definitely going to push current that way. The IC looks like a good direction because this 15-volt battery should push current that way. Those currents both match batteries. But what we find is for IB, this middle current right here, this current isn't at all obvious because you could have this flow come back up, and this is a stronger current flow because we have a larger battery and they have the same